So I'm going to be talking about counteracting selection bias in machine learning. So the data that we use in machine learning are collected in all kinds of ways. And we usually pretend they're collected at random. They're collected without selection bias. This can cause us problems, and I'll show how that might come to pass. And then I'll suggest a few ways that we could model the data collection process instead of assuming that it's at random to overcome some of those problems. So the takeaways are I want to understand the importance of selection bias in machine learning. This is something we talk about a lot in statistics, and that's because we're trying to understand something true about the world. We're trying to estimate a parameter that represents a fact. And if we have selection bias, we'll get our facts wrong, and that causes problems. We're not doing that in machine learning. We're doing prediction. And so people often don't think about this as much as they should, but it still matters. We want to figure out how to know when our data does have this problem and what we can do about it. And then there's a last piece, which is, in some cases, if we have a small subset of data that is collected at random that doesn't have selection bias, we can use that data to learn about selection bias in the rest of the data. OK, so let's talk about data collection. So data collection happens in two steps. Step one, things happen, events happen in the world. Right, so I work in medicine a lot, so we have patients with elevated heart rate. Maybe they go on a bike ride. Maybe they have a temperature. They take medication, whatever the case may be. Step two, some of these events that have happened in the world get recorded. We see some of them. Right, so people often think about step two as the only place selection bias can occur, but it can actually occur in step one as well. So let's just define what we mean by selection bias in this talk. So I'm going to mean correlation between how likely we are to see a particular data point, x, y, that's the features in the outcome, and the outcome y. So if we're more likely to see a data point with a high outcome or with a low outcome, then we have selection bias. So here's an example of how you can get selection bias in step one before you've even recorded anything. So let's say we're asked to create a tool that helps project managers predict profit for software projects. Right? This kind of stuff happens all the time. Our data include all of the software projects that have ever been undertaken in our company. So we're not missing anything. But it turns out that project managers are pretty good at their jobs. And so we don't get a lot of projects with low profits. Right? So there's a correlation between how likely we are to see something and the outcome. Low profit means we're unlikely to see it, even though we actually do see all of the data that's available. So just to illustrate this point, we have, let's say, profit on the y-axis, project complexity on the x-axis. So this is sort of a proxy for all of the different kinds of input features we would want for a problem like this. Approved projects are in purple. Rejected projects are in red. So these are the projects that would have happened had they been approved and what their profit would have been. So we can see they're clearly different. And they're different in a systematic way. So this is a little bit troubling. Obviously, no machine learning model can learn about this decision boundary if we don't see the red projects. And this isn't just a problem of extrapolation, which we'll see a little bit later on as well. Even though nothing is missing in the strict sense of missing, we've seen everything that happened. And this is a really bad way to fail. In particular, we're going to overestimate projects for profits for projects that are going to do badly. There's something we can do about this. So we started off this scenario with a story about why data are generated the way they are, which is that project managers are good at their jobs. And so we know something about the selection bias story. We can incorporate that into our model to overcome this problem. OK. You can also obviously have selection bias in step two, which is in what you observe. So this is an example from my field. So we have white blood cell count normalized on the y-axis, time on the x-axis. White blood cell count, high white blood cell count is often indicative of inflammation or infection or causes of feeling poorly. And we know in medicine that patients come into the clinic when they're feeling poorly. So the X's here are clinic visits, recordings of white blood cell during clinic visits. And the blue dotted line is the truth. And we can see that the blue dotted line is much lower when we don't have any clinic visits. So we only see the outcome of interest when it's high. So that's a selection bias, even though it does happen everywhere else as well. OK, so how do we incorporate this knowledge into a machine learning model? So in general, we're trying to model the expected value of y given x as a function g of x parameterized by beta, where g is whatever class of functions we want. So it could be a neural network. It could be a decision tree, kernel regression, whatever we like. And we can do this because it's tractable because y is one-dimensional. So we don't have to think about too many things at once. If we want to model data collection full stop, we have to model this quantity here, p of y and x. So that's how likely we are to see an observation y and x. And that's really hard to do for two reasons. One is x is highly dimensional. So now we have to worry about a lot of things. We have the curse of dimensionality. And we're trying to model a density. And densities are complicated. In problems that we care about, in machine learning, we can do this. The probability of making an observation is a function only of the outcome. So we told a story about white blood cell count, and we told a story about project management, where how likely we are to see something depends only on the outcome, doesn't depend on other things. And so if we're willing to say that, which we can say in machine learning because we don't have to worry about specifying things exactly correctly.
If you want to head in 5 minutes just to make sure you're good to go.
Sorry? Did everyone hear that, or was that just me? OK. I'm just going to keep going and assume someone will tell me if something's wrong. So we only record the part of the likelihood of making an observation that is a result of the outcome y. So we modeled the whole probability of seeing an observation as just a function of y. And that simplifies things dramatically. We're back down to one dimension. We can handle one dimension. At test time, we don't see y, obviously. But we can estimate the probability of seeing an observation with this plug-in estimate, where g is the regression function as before. So how do we actually incorporate this knowledge? So this is one way to do it. Let's say j is the negative loss function. It now has two pieces. L1 is the outcome loss. That's the usual loss. You pass it your estimate and the outcome, so the quantity you're trying to estimate. And you see how far apart they are for some definition of far that's appropriate to your problem. And then there's the observation loss. And the observation loss is high if we don't see a lot of observations where we expect to, or if we see a lot of observations where we don't expect to. And it's low if the observations happen where we expect them to happen. OK, so what does that look like? Well, going back to the previous example, if all we see is this data and we fit a regression to it, of course, this is very simplified, but we might get a regression that looks kind of like this, straight line. Now, we can learn from what we don't see. So we had some knowledge ahead of time, and we can use it. We know there are regions of the input space with no data, high project complexity. We know we're less likely to see data with low profit. We infer profit must be lower in those regions where we don't see data. And if we incorporate this knowledge, even without seeing the things that we don't see, we'll get a regression function that looks more like this. And this is closer to the truth. OK. What if we don't know the data collection process? So up till now, we've had a story about what the data collection process is. What if we don't know it? Really important point, we can't learn it entirely from data, because that would require us to know the outcome exactly where we don't know it. So this is something we need to bring some knowledge here, in most cases. So I'll talk about the other cases in a minute. If we have beliefs about the data collection process P and the regression function G, we can be Bayesian about things. And that actually turns out to be very useful, because often we won't know exactly what the data collection process is, but we'll have some idea it should be higher. Selection bias should correlate to high outcomes or low outcomes or something like that. And so we can incorporate those beliefs into the model and improve that way. And if we have just a few data points that are collected at random, not according to the data collection process P, we can learn about the data collection process P. And so I'll illustrate that point in a minute. So let's go through an example of all of these claims. So we're back in the white blood cell count setting. Let's say we have some unknown non-random data collection process that gives us these observations. So the X's are the observations. NAR stands for not at random observation. So we can't learn about the selection bias from the data. And this plot illustrates why. We have two potential regression functions, green and, let's say, maroon. And they both fit the data really well. We can't distinguish between them based on the data itself. But they imply very different things about selection bias, right? So if the green function is true, then we're more likely to see the data when the outcome is low. But if maroon function is true, we're more likely to see the data when the outcome is high. And we can't tell which one's which without any other information. So we need to bring something else to the equation. OK. Let's say we do the usual thing, right? So we fit a model, we have some data, we fit a regression function, and we assume that the data is observed at random. This is that if you ever fit a neural network or you fit a Gaussian process, unless you do something special, this is in general what you'll be doing. Data looks good. The fit looks good, right? So we're going right through the X's. If we had validation data collected according to the same observation process, we still wouldn't see it in the places where we don't see this data. And so the fit would continue to look good. Validation data is not going to solve our problem here. If we can see the truth, again, the truth is the dashed blue line. The prediction is the black line. If we can see the truth, it turns out that we're systematically way off. And it kind of makes sense, because if you look at, there's the first big dip between, let's say, 2.5 and 7.5 weeks. If you look at those two data points, the prediction is just kind of thinking, well, the regression function is going to climb slowly from the first one until it reaches the second one. And then it's going to hang out there. And unless you know something about selection bias, there's no reason to think that it would do anything different. So it might seem like, well, maybe that's clearly not what we should be doing in this case, but this is kind of what people do. So this is something to think about. Let's say we have some beliefs. So we don't know exactly what the selection bias is, but we have some beliefs about what we think is likely to be true about patient behavior, such that we collect data that looks like this. This is a demonstration of incorporating those beliefs. And so you can see, because we're not giving it the exact selection bias model, we're not getting it exactly right. But if you compare it to the previous slide, we're doing a lot better. So in regions of low observation, we're, first of all, much closer to the truth. And second of all, the confidence intervals are doing a lot better. And so now I'm going to come to the last point about what happens if you have a small subset of at-random data. So let's say you don't know what you think. You don't have any stories about what the selection bias is. You don't have any beliefs. You don't have any priors. But you have some story for why a small subset of your data is at random. So at random here is represented by circular observations. Not at random is by the x's. So in medicine, this happens because, for all kinds of reasons, but for one example, if we have patients in hospitals, their vital signs get measured pretty regularly. But the vital signs are measured primarily because the patient has called the clinician because they're not feeling well. The clinician comes in and takes their vital sign, or a family member has called them, or the clinician sees the patient's not doing well. And all of those measurements happen because of something about the underlying patient state. The patient's not feeling well. So we have selection bias there. But it's also true that in a lot of hospitals, there's a policy that when nurses first come on shift, the first thing they do is they make the rounds and take vital signs for all their patients. So that data was not generated, was not observed for a reason that's correlated with the underlying outcome. So we could treat that small subset of data as at random. And you can come up with stories like this in lots of different domains if you think hard about it and you're sort of clever about how you approach your data. And once you separate out the not at random and the at random data, it can tell you some pretty interesting things. So in this case, a lot of these at random observations turn out to be useful. The one all the way on the left is sort of exactly in the same place as the not at random observation, so that one doesn't tell us anything new. But the other ones give us sort of a window into what the true function is doing when we couldn't otherwise see it. It turns out that when we don't see it, the true function is kind of lower than we think it is. So if we go back to this slide, we can't choose between green and maroon purely from the observed data. But if we have the at-random data, and we see that it's lower than we kind of think it is, well, that gives us a reason to choose the maroon function over the green function. So that's what the at-random data gives you. And when you have it, you can learn about the selection function. So here's what happens if you use the at-random data to learn about the selection bias in the rest of your data. So obviously, this fit is a lot better. And it's important to distinguish there are two reasons for it to be better. One is, well, we now have at-random observations in the first two dips that we didn't have before. So it's just, we shouldn't put too much weight on that improvement, because that's just due to seeing stuff that we didn't see before. But what we should put weight on is the third dip, where we don't have any data. We get much closer to the truth than we were before. And that's because we've learned the selection bias function. We've learned that if we don't see something, it's because patients have stayed away from the clinic. And if they've stayed away from the clinic, it's because they're feeling well. And if they're feeling well, then they're unlikely to have infection or inflammation. But blood cell count might be low. OK, so conclusions. Selection bias in machine learning matters. It hurts us in ways that we can't detect through normal validation procedures. If we know something about the data collection process, we can incorporate that information into the model to improve performance, in particular to improve it in regions of the input space where we don't have a lot of data. And if we happen to have some data collected at random, we can use it to learn about selection bias in our data. That's all I got. I think I'm a few minutes early, so if there are questions, I'd be happy to take them.
Hi. So thanks for the insightful talk on biases, beliefs, and how to incorporate them. One of the questions I have is you spoke about beliefs before putting the final data points in, and kind of showed that the belief followed the real curve really well. One issue there is if you're in a system where you cannot collect data, like if you didn't have the red lines, then you could also be biased in your beliefs.
Yep.
So what's a good way to explore multiple beliefs? And then, of course, what if you don't have data in that space at all?
Yeah, so if your beliefs, it's always the case if you have bad priors, you're going to get bad posteriors. So this problem is really tricky because to get information on it, you have to see the outcome where you don't see it, and that's really hard to do. So if your beliefs are bad, you're going to be especially susceptible to getting bad posteriors. And so the word of warning there is to only try to do this, only put priors on these things if you're pretty sure you know what you're doing, or you have a small at-random subset of data. The other thing you could do, which we didn't look into in great detail, is sometimes you do get observations that are not at random. Sometimes patients are feeling unwell, or they come into the clinic for, maybe they're about to go on a long trip and they want to come into the clinic to get checked out. So you do get an observation in a dip anyway, but you get those with low probability. That's the point of selection bias. And so if you want to do some kind of validation, a trick in statistics that they use is to upsample the observations that you see with low probability. And if you upsample those enough in your loss, then they'll show you how you would have done had those kinds of events happened a lot more. But to do that, you do need a propensity model. So the short answer is it's complicated. It depends a lot on your situation.
So how do you know that your AR data is actually random? Because it's not. It's biased, but in different way. Because your shifts can be at certain time or whatever.
Yeah, no, that's a good point. The same kind of answer goes, is you need a pretty compelling story for why you should believe that they're random. You can kind of check your story, right? So if you pick all of your data that you think are at random, and you look at their distribution at large, and it has the same distribution of data that you think is not at random, well, then it's probably not any different. But if the distributions are different, then there is a systematic difference. And the question is just, is it the correct systematic difference? And that's another thing that you can't validate from data.
Awesome. Thank you, Noam. That's it for questions. You got your contact info somewhere so they can follow up with you?
Yes.
Or it's also on the website?
Yep. Come talk to me. I'll be around. Thank you.